Okay, so here we are, Intro to Machine Learning. And I'm going to start with a quick introduction to the course, what it's about and what machine learning is about. After that, I'll go back to the conventional first day stuff, syllabus, and all of that. So today we're going to talk about what machine learning is. We'll talk about what kind of problems machine learning is well suited for and what kind of problems it's not well suited for. We'll discuss a little bit of terminology and kind of give a general framework for all of the machine learning methods we'll learn. And then we'll put a little bit of a reality check on everything we just discussed. So our first question is, what is machine learning? And I have here this definition according to the comic XKCD, which defines machine learning basically as a big pile of linear algebra. But I'm interested to know what you think. Since you all signed up for this course, you must have some idea of what machine learning is. So what do you think machine learning is? What makes something a machine learning system? You can go ahead and type answers in chat. Okay, so Ben suggested an algorithm that changes over time depending on the input it receives. I'm so glad you said that because we'll talk about whether that's always the case or not. Evan says improving prediction algorithm using data. Yeah, that's very close. And Priya also says a predictive model based on data. Now, it's not clear what we mean when we say things that are based on data. So to answer this question, we're going to maybe look at a few examples, and then you'll let me know whether you think I've described a system that's a machine learning system or not. Right? So I see a lot of people discussing algorithms based on data. That's really good. Okay. So I'll describe a few problems or a few systems that solve a problem. And you're going to tell me whether the system I've described is a machine learning system or not. Okay. So first of all, generally speaking, I'm going to use this little whiteboard here. When we solve problems using computer systems, we program them to, let's see, get some input from the world. I'll draw my little world over here. Okay, excuse my terrible drawing. Here's my little world. Get some input from the world and then use it to produce some sort of actionable information for the world. And this is true, generally speaking, not only for machine learning systems, but let's put a little machine learning system in here. Okay, so here's my machine learning system. And it's going to get some input from the world. That's a bad color. That's better. Okay, it's going to get some input from the world and produce some actionable information that can then be used in the world. Okay. So suppose I want a system that will help students decide whether or not to enroll in this course. And as input, the system will accept grades on previous coursework. And the actionable information it will produce is, what is my predicted machine learning course grade? Okay, so back here, the input it gets from the world is course grades on previous courses. And then we're going to ask it to predict my course grade. Okay. Now, that's kind of a little awkward to think about how a computer system would use it. Let's mathify it. Okay, so we're going to let x1, x2, and x3 be my grades on previous coursework. x1 is my previous probability grade. x2 is my previous linear algebra grade. And y hat is going to be my predicted ML course grade. And here the y hat implies that it's an estimate. Okay, so y hat is my predicted course grade. And my course grades on previous courses are going to be, we can think of it as like a vector of 3 previous grades, x1, x2, x3. And then we have this machine learning system, which we'll call a system F. Okay, so now we have our framework set up. I'm going to describe a few variations on this. So first of all, suppose we predict the grades as the minimum of the 3 previous coursework grades. So suppose I say, well, all of these prerequisites are so important for machine learning. A student who's weak in them is probably not going to do well in the course. So I'm going to predict your machine learning grade as the minimum of your previous coursework grades, so the minimum of X1, X2, and X3. Okay. So now I have a question for you guys. Is this a machine learning system? Okay, take another few seconds to answer. All right, so the course was split 50-50. Half of you said it is machine learning, half of you said it's not. I'm interested in hearing why it would or wouldn't be. So somebody who thinks it is a machine learning system, can you explain in chat why it is a machine learning system? Okay, so Evan says, well, since it's based on past grade performance, that makes it a machine learning system. Okay, any other reasons why it is machine learning? Okay, somebody who thinks it's not machine learning, tell me why it's not machine learning. Okay, Michael says, well, the performance could be good in ML even if you did bad in other, independent of other subjects. That might be true. That's not clear whether that has any impact on whether or not it's a machine learning system. You could have machine learning systems that are good or bad at what they do. Oh, sorry, Michael said because machines don't learn anything from previous data. Yeah, that's a very good point. Okay, well, we were a little split on this one. Let's try a different example, and we'll see if we get a little bit more agreement on this one. Okay. So suppose instead of predicting our grade as a minimum of 3 previous grades, now we're going to predict the grade as the weighted sum of your 3 previous grades. So let's say we say your predicted course grade in machine learning should be based half on your grades in previous math courses and half on your grades in previous programming courses. So we'll give 1/4 of the weight to linear algebra, 1/4 of the weight to probability, and half of the weight to programming. Okay. So now we have 1/4 x1 plus 1/4 x2 plus 1/2 x3. So this updated system that predicts your machine learning course grade as the weighted sum of previous course grades. Is this one a machine learning system? What do you think? Okay, take a few more seconds. Okay, so let's see what you said. About a third of the class said this is a machine learning system. Can somebody who thinks it is a machine learning system explain why it might be a machine learning system? Okay, and then 2/3 of the class said it's not a machine learning system. So in the chat window, tell me why you chose the choice you did. Why is it a machine learning system or not? Okay, so Farhan says we're inferring based on the data we have what the predicted grade could be. So that makes a machine learning system. The next comment says the weight should be something the machines learn. That's rather than something that we give. That's a good point. And Greg agrees the weights are static here. And Daniel says the function has a fixed definition before any data is passed through. Okay, so the majority here said this is not a machine learning system. Let's see what you think of the next one. Suppose we predict your grade as the mean of last semester's grades. So we're going to predict your grade as W0, where W0 is the mean of last semester's grades. So now we're actually completely ignoring the input. And instead, we're going to use a mean of last semester's grades. So let's put last semester's students in here. We had some very eclectic students last semester, as you can see. Okay, so now I'm going to predict your grade as the mean of all these other students' grades. Is this one a machine learning system? So now I'm totally ignoring your grades on previous coursework, X1, X2, X3, just predicting your grade as the mean of previous semester's grades. Okay, it'll take about 5 more seconds. Okay, so here too, the results are similar to the last question I asked you. About a third of you said it is a machine learning system, and 2/3 said it's not. So I'm interested in hearing people who changed their vote between the last system and this system. So someone who thinks that the weighted sum of previous course grades was machine learning, but this is not, can you explain why? So why was a previous system a machine learning system, but the current system is not a machine learning system? Is there anyone who changed their vote? What's the difference between this system and the previous one? Is there anyone who changed their vote the other way? So said that the previous system was not machine learning and this one is. Okay, no one changed their vote, fine. So tell me about your logic if you thought that, okay, some people did change their vote. So Melissa said, let's see, this is a static function, so it's not machine learning. Let's see, so you mean the mean is not machine learning because it's a static function. Okay. Thrishi says, well, the input is ignored, so it can't be a machine learning system. Maybe. Let's see. Okay, any other comments on what makes this particular system machine learning or not? Okay, Disha says, well, it's learning from its previous experience. So here it's learning from the grades of previous semesters. Okay, therefore it's a machine learning system, maybe. Evan agrees it's a fixed formula, so it's not machine learning. Okay, let's see how you all feel about the next one. Now, in this one, my algorithm for predicting the grade is as follows. We're going to find the set of grades of 3 students from previous semesters who have a profile most similar to yours, meaning the most similar probability, linear algebra, and programming coursework grades. And then we're going to predict your grade as a median of their grades. Okay. So suppose these 3 students from previous semesters were pretty similar to yours. And this one is the median of those. And we're going to predict your grades as a median of those 3. Is this one machine learning? Okay, this one gets the most votes for machine learning, more than any other previous system. 70% of you said it's a machine learning system, 30% said it's not. Tell me about your reasons. Why is it or is it not a machine learning system? And in the meantime, I'm going to be writing things here based on your comments in chat about what is and is not machine learning. Okay. Okay, so let's see what we had to say about this one. It's machine learning because it learns from previous data, other students' profile and grades. Maybe it's not machine learning because it doesn't get feedback to learn and improve the algorithm for the next iteration. Ben says it will behave differently depending on what inputs are passed to it. Okay, let's see. It's using another set of data points to create as output for new data. Students similar to our profile also input and weighted in. Okay, let's see. Braden says, if the system is to determine the profiles most similar, I can see how that would be machine learning. But if it's given as input, algorithm and weights are still static. So in that case, it's not machine learning. Okay, a lot of disagreement here. Let's look at some of the comments that we've had in chat about whether a system is or is not machine learning. And let's think about whether or not they're strictly required in order to be machine learning. Okay. Now, first of all, I want to differentiate between two kinds of data. Okay. There's one kind of data here, that's my x1, x2, and x3. And that's the input I'm using to get the current prediction. So that's, let's say, data related to my current test sample. So suppose I have a potential student in this world that we're interacting with. And I have the data that relates to the student who's the source of the current input, and then the prediction for that student. And then I have another type of data. My other type of data is data that's not related, that's not part of my current input. Okay. So I have data from previous semesters, and I have the input data for the current sample. Okay. So now when we look at these comments, let's look at what kind of data we're referring to. So this is a comment from the beginning when I asked, what is machine learning? And someone said, it changes over time depending on the input it receives. Do we mean it changes over time depending on the input from the current sample? Or do we mean it changes over time depending on the input from, let's say, all these other examples? Okay, let's try and clarify that a different way. So let's think about what a system would be to do this that's not machine learning, right? If I would go ahead and write a computer algorithm that would accept some inputs and produce some outputs, that doesn't necessarily make it a machine learning system, right? So let's actually describe something called a rule-based system. A rule-based system is one where you develop an algorithm that produces your desired result for a given input. Okay, so you can have some input to the algorithm. For example, x1, x2, x3, that's input. Then you implement the algorithm in code. You feed the input to the algorithm, it will output a result. Okay. So with that in mind, if we, let's say, produce some output based on input data, right, that's true of a rule-based algorithm also, so one that's not machine learning. So this is not necessarily uniquely a feature of machine learning systems. Right? So this input here, x1, x2, x3, this is the input for the current sample. Right? And inferring an output based on the input data is not uniquely a feature of machine learning. Right? Ben said machine learning algorithm might give different results with identical input. Let's see if that's true. Okay, let's see. So statistically inferring based on input data, not necessarily uniquely a feature of machine learning. A rule-based system will also infer something based on input data. And the fact that it uses statistics doesn't necessarily make it machine learning. Okay, let's see. So an algorithm based on past grade performance. Is that uniquely machine learning, or can I make a rule-based algorithm that's not machine learning based on past grade performance? Okay, so I can make a rule-based algorithm where the input is past grade performance and it outputs my desired result, but it's not necessarily machine learning. So this is also not uniquely a feature of machine learning systems. Okay, let's see. Now we have some things where some people said that either the system does or does not do those things, and so that disqualifies it from being machine learning. There were some systems where the input is ignored. Does that necessarily disqualify it from being machine learning? Is it possible to have a machine learning system where the input is ignored? Well, let's say we want to train a machine learning system to predict a grade as well as possible, and I'm not even going to tell you any details of how it does it. But let's say that so far, every student who has ever taken my machine learning course has earned a 95%. Now, suppose I would then train a machine learning algorithm to predict my course grade based on my grades in previous coursework. What do you think the output of that system should be? Okay, so that system should produce a 95 for everyone, because if it's learning from previous data, which hopefully it is, it will understand that the output that minimizes error is 95, because that's the value I've given to everyone. So it might be okay for it to ignore the input. If the input is not relevant or not necessary for determining the output, let's ignore it. Okay, so it doesn't necessarily matter if we ignore the input. I mean, we usually use input, but maybe we don't strictly have to. Okay, let's see. Changes over time depending on the input it received, or giving different results on two passes with identical inputs. Braden asked, does the training not count as input? So here we're specifically kind of differentiating between, let's say, the input for the current sample and maybe some other stuff that it has, like here. So we're going to call this input for current sample. Okay, so when we said the input was ignored, this was a complaint someone had about the system that predicts the mean, where it ignores the input for the current sample. But that's not necessarily disqualifying. Okay. What about changing over time depending on the input, or giving different results on different passes? Now, it's true that a machine learning system might do that, but does it have to do that? Okay, so it could do that, doesn't necessarily have to. Could a rule-based algorithm change over time or give different results on different passes? So I think it could. Let's say there's grade inflation over time, and so I develop an algorithm where one of the inputs to the algorithm is what year it is. And maybe depending on the year value, I might give a different predicted grade. That's a rule-based algorithm. So it's possible for a rule-based algorithm to give different outputs over time. And it's also possible for a rule-based algorithm to give different results with identical inputs. So I could even build some randomness into my rule-based algorithm, where I'll probabilistically return one value or a different value depending on the input. So these are possible for machine learning systems, but again, they're not necessarily unique to machine learning systems. Okay. Let's see, what are we left with? Feedback improves the model for the next iteration. Is that required for a machine learning system? Well, I would say this is something that is probably neither required nor unique to machine learning systems. You could implement a machine learning system and then never touch it again and have it run for 10 years. That's possible. And never have the actual model be updated. It's also possible to have an algorithm where you kind of have a human audit every few years and you improve it. So I'm not sure that this is necessarily either unique to machine learning or required. Okay, so what's left? We're left with model based on data. Let's say the question of whether weights are fixed or not fixed. Now, in the last example where we took the median of 3 previous grades, there was no weight. Right? So I'm going to put this in gray because, well, we said that we couldn't potentially have a machine learning system with no weights at all. So we can't necessarily use weights to distinguish machine learning systems. Okay. So we're left with model based on data and learning from previous experience. Okay. Now let's distinguish between two things with respect to learning from previous experience. Suppose I, as a developer of my rule-based problem solving, have a lot of previous experience. Right? I personally have plenty of previous experience teaching machine learning. So I can use that experience to develop an algorithm that's pretty good. Does that make it machine learning? So using my human expertise and previous experience to develop an algorithm actually does not make it a machine learning system. When we say that it learns from previous experience, we mean the model itself learns from previous experience. So not that the human developing the model has previous experience, but the model does. So it's a little confusing. I'm going to put that in gray too. And we're left with the model is based on data. So in these 4 systems we just described, let's mention them here. So we had a median, we had a mean, okay, then we had a min, and then we had a weighted sum. Which of these would you say is based on data? Okay, so they're all based on some sort of data, that's true. Let's kind of distinguish what kind of data they're based on. So I'm going to make a chart. Whiteboard's getting a little crowded. Okay, and let's see, which ones are, actually, this is not going to be a chart. It's going to be a Venn diagram. I haven't used one of those in a while. Okay, so this top one is based on current input. And bottom one is going to be based on past data. Okay. The one that was the, let's see, mean of last semester's grades. And that one based on the current input. No, it's based on past data, but not current input. Okay, so we'll put it in there. Let's say the one that's the min of x1, x2, x3. Is it based on current input, past data, or both? Okay. So the one that's min of x1, x2, x3 is based only on the current input, right? So the input from this woman over here. It doesn't necessarily use any past data, except insofar as I myself, the designer of the algorithm, have past experience. But we're not including the algorithm designer's past experience as past data. So it doesn't count. Okay, what about this one? The weighted sum of course grades. Is this based on current data, current input, past data, or both? I'm going to put it here. It's based on current input. Okay. And then the one where let's say we use the current input to find the three previous students who are most similar, and we predict the median of theirs. Okay, so this is both. So here we have 2 systems based on past data, 3 systems based on current input. What do they all have in common? Is there anything that all have in common? Okay. I'm going to say all of them have some structure that's fixed by a human designer. So I myself am the human designer of all these systems, and each of them has some structure to them in which that's fixed by me. But some of them have some parts of it determined by past data, some of them do not. I'm going to say that these 2 here are machine learning systems. So these 2 systems, which are based on past data, I would consider these machine learning systems for exactly that reason. So because they use past data in order to determine how to process a current input, I'm going to consider it a machine learning system, as opposed to these other systems where I might have used my human expertise and experience to develop rules, but the rules itself, the algorithm itself, does not actually make use of any past data. So it doesn't refer to any past data. It doesn't refer to anything that it computed from past data. It just follows the rules for the given input. Whereas a machine learning system will have been trained or built using some prepared previous data. And in both cases, we can use a model, on new input to produce output. Okay. So these things are common to both the rule-based systems and the machine learning systems. And some of the machine learning systems use the current input, some of them did not. But what they have in common is that the machine learning systems use past data. Okay, let's go back here. So the first 2 systems I gave you were examples of rule-based problem solving where I use my domain expertise and my knowledge to establish rules for solving the problem. For example, I use my expertise to say the minimum is a good choice because students need strong grades in all their previous coursework to do well. In the second 2, I still use some of my own expertise. So let's say my expertise might have told me, oh, it doesn't actually matter what your previous coursework grades are. The best estimate of what your grade is going to be what grades have I given out recently. Or maybe my expertise tells me, yes, your previous grades matter a lot. And so to estimate your current grade, your predicted grade, you should look at similar students who had similar previous grades. So I'm still using my own expertise to establish rules. And the rules I established determine the structure of the solution. So the rules I established are basically responsible for describing what that system F looks like. But in the machine learning systems, I'm also using data that's not from the current input to produce output. Are there any questions about those 4 systems and what makes them machine learning or not? If you have a question, you could go ahead and type it in the chat. Okay, so we have these machine learning systems, non-machine learning systems. What are some benefits of using this data-driven approach? So the machine learning systems are data-driven, and that they somehow use previous data in order to produce the output. What are some benefits of that? Michael says it's more accurate, and maybe or may not be, right? So take the system that determines your grade as the mean of last year's grade, right? That will be a very accurate system if I did, in fact, give the same grade to everyone last semester and give the same grade this semester. But if, as is typically the case, there is a range of grades in the course, then it's not necessarily going to be very accurate to predict the mean. Right? Okay, Farhan says, it can learn things that could not be obvious to us. Maybe. Some of these, I don't think these particular machine learning systems would learn anything that's not obvious, right? So the mean of previous coursework is a machine learning system because it's built using data as part of the model itself. But I don't think it learns anything that's not obvious. Right? Similarly, the system that uses a median of similar students, that's pretty obvious. So maybe it could learn things that are not obvious, but these systems do not. Is there any benefit to these systems in particular, or let's say relative to the ones that don't use data? Okay, well, Evan says, it can help us solve problems that are difficult to hard code. Yes, that's very true. So for some problems where humans cannot easily take their own expertise and put it into a program, like the handwritten digits, machine learning can be helpful. But what about these particular systems? So the median and mean systems. Is there anything about these particular systems for predicting course grade that are especially good? So it does require less human expertise. Yes, that's true. So the first systems required some human expertise to decide what would be a good rule. The median system at least does not. Daniel said the mean system doesn't require manual input of data. Well, I think in both cases, oh yeah, you mean it doesn't require any input. Yeah, that's true. Okay, I'm gonna make a suggestion. What happens if the world that we're in, meaning this world right here, changes? Right? So suppose that, let's say, one semester I give out 95s, but then over time I start to have some complaints from students that they're insisting on higher grades than 95. And maybe I start giving higher and higher grades over time. Right? Which systems would adapt to it? Would this system adapt to me giving higher grades over time? So the system that just has predefined rules, whether it's a min of previous grades or weighted sum of previous grades, it's not able to be easily updated if I gain more experience or if the world changes. So if the world changes, then I need to manually update the rules. It won't necessarily happen automatically. Whereas these, which use data from previous semesters, as long as I keep feeding it data from subsequent semesters, it will be updated automatically without me having to hard code new rules. What about if, let's say, I initially don't have many students with poor programming background? So maybe this might be a good rule as long as it applies to only students with a good programming background. But the truth is that maybe for students with a poor programming background, the min rule is not a good rule. Okay. So maybe I should really have one rule for the min students, for the strong programmers, and one rule for the weak programmers. One benefit of the system that's based on data is that as I collect more data about students who come into the class as weak programmers, my system can improve by using the new experience. So for example, this median system, maybe initially it's not going to do a good job on weak programmers just because I don't have any in my sample. But as I accumulate more data for more semesters, I'll accumulate more samples of those rare examples, let's say students who are weak programmers, and then I'll do a better job predicting it. So these two systems are kind of easy to update with more experience or if the world changes. Whereas the first two, which are hard-coded rules, require manual updating of the rules if the world changes or if I get more experience. Now, someone brought up the example of recognizing handwritten digits. Okay. So this was a challenge that we read an article about before this class, hopefully, but if not, sometime this week. So I shared with you some information about an exhibit at the 1964 World's Fair. My mother went to that. She told me she went about a dozen times. Very exciting. And at that exhibit, you can write a date on a card and put it into a computer, and it will tell you the New York Times headline on that date. Now, in the notes I gave you to read, I described the system in some detail. So now I have a question for those of you who read that article. Was the system described in the notes a machine learning system? Based on the definition we've just given. Okay, take a few more seconds to vote if you've read that. Okay, about 2/3 who voted said it is a machine learning system. Why? So here's some information about how it worked. First, it would try and determine the contour of the digit. Then within each region of the digit, so there are these 12 regions, it would try and determine the direction of the line. And then there was a circuit here that looked for certain line directions in different regions. So for example, here the circuit first looks for the line going this way in row 2. And if that's satisfied, then it looks for the line going this way in row 4. Then it looks for the line going to the right in row 4, and so on. So after detecting each particular line that it's looking for, it goes on to the next one. So Ben says it uses past data to learn how to process new inputs. Ben, can you clarify what the past data or new input is? So what's the past data here? Okay, so it's true that this system was developed from 3,000 handwriting samples. But did a computer process the handwriting samples to determine these rules, or did people determine the rules after looking at the samples? So this set of rules here, so here's a set of rules, shape features that the designer has identified for each character. And these rules or features for each character were developed by experts based on looking at many samples of each digit. So if the rules are developed by experts, we consider it a rule-based system. And it's a little confusing because machine learning systems also have rules, and they can also be developed by experts. But none of these were kind of developed by computers. So we didn't ask a computer to look at these 3,000 samples and determine what shape features are in each character. We had experts do it. So that would make this a rule-based system that's not a machine learning system. The experts used a lot of data in order to decide how to develop the rules, but they didn't give the data to the computer. They only gave the rules to the computer. And they even said specifically that they use subjective judgment to decide which rules to include and which not to include. So a bunch of experts got together and thought about what a 5 should look like. And if there were samples in the set that didn't look like what they thought a 5 should look like, well, they didn't really care about recognizing those 5s. So this system was actually not a machine learning system. It had rules based on previous data, but those rules were developed by experts, not by machines. So I would consider this not a machine learning system. What do I think of the fact that experts instructed people how to write a number? That's a good question. What do you think of that? Mhm. So there's some disagreement over which problem is more difficult, the handwritten digits problem described here, or let's say the problem of recognizing the digits shown here, which come from a more standardized data set. So one thing that's interesting is that one of the goals here was to be able to detect the handwritten digits no matter where they were within a larger area. So actually the writers had a lot of flexibility in terms of where to write the digits on the card or how big the digits could be. Now there's another very popular data set called MNIST that's shown here, and that's often used to train machine learning models. And that data set is, this data set shown here, MNIST, is already pre-processed, which means that all of the digits are already scaled and resized to fit in the same kind of area. So when you work with MNIST, you don't really need to care about, let's say, where the digit is in a broader area. You also don't need to care about how big the image is because they've been pre-processed for you. So that actually makes this MNIST data set shown here kind of an easier problem. Whereas in the problem here, well, yes, they did give some instructions, you could say, about how to write the digits. For example, they said, don't use any fancy curls or lines. But I think that's okay. Okay, are there any reasons not to use machine learning for the handwritten digit problem? So we said this is a good candidate for machine learning. I'm going to write this down. A good candidate for machine learning because it's difficult for humans to encode their expertise in a program. Right? We saw that you could attempt to, let's say, define what are the shapes that make up, let's say, a particular digit. And you can attempt to encode that in a program, but it's difficult and it's very fragile. Are there any reasons why this is a bad candidate for solving with machine learning? Okay, I think this is a pretty good candidate for machine learning. Let's look at this one, autonomous driving control. So imagine a system that takes camera input and produces some output that tells the car autonomously what to do. Is this a good candidate for machine learning? And if so, what makes it a good candidate? Let's do a poll. Is autonomous driving a good candidate for machine learning approach? And when I say good candidate for machine learning approach, I mean compared to, let's say, implementing a rule-based algorithm. Okay, take a few more seconds. All right, most of you said this is a good candidate for machine learning approach. I would say this is another example where it's difficult for humans to encode their expertise into a rule-based system. So it's very complicated to, let's say, figure out how to program a car with all the rules that humans use in a rule-based system without using data. Now, are there any reasons why it might be bad to use machine learning for autonomous driving? Okay, Farhan said there are ethical concerns. What are the ethical concerns? Well, let's think about autonomous driving in comparison, not to a rule-based system, but in comparison to a human driver. Okay. So I think we could all agree that a rule-based algorithm that doesn't use data is a terrible idea for autonomous driving. A machine learning algorithm would definitely be better because it's impossible to program a rule-based algorithm complicated enough. But what about a comparison between a machine learning-based autonomous driving car and a human driver? Okay, so some people mentioned safety. So some problems with, let's say, machine learning-based systems is, yes, that Melissa mentioned this. A human driver is pretty good at generalizing to things they have not seen before. Right? So when you look at the notes for this after class, I refer to an article about kangaroos. Apparently, kangaroos behave very differently from other animals on the road, which means that a machine learning algorithm that's trained to deal with other animals doesn't know what to do with kangaroos. Now, if you're a human and you've seen other animals on the road, maybe a deer, a raccoon, if you've dealt with other animals, you know what to do when you see a kangaroo. If you're a computer and you've never seen a kangaroo before, it's not necessarily clear to you what to do. So computers try and generalize to new generalities. Computers can try and generalize to new situations, but they're not always going to make the right choices in new situations. Now, you could say, well, you could program a machine learning car to just never hit anything in the road. But it's a little more complicated than that. First of all, a machine learning car shouldn't stop if there is like a newspaper in the road, for example. So you don't necessarily want it to stop for anything in the road. And also, the machine learning car needs to be able to make predictions about how things move. So a machine learning car should understand that if there's a stop sign on the side of the road, it's not going to jump into the street. But if there's a kangaroo on the side of the road, it might jump into the street. So there's this concern that a machine learning system may not generalize to new unseen situations as well as a human could. And there's also concerns that machine learning systems can sometimes be tricked by some attacks that won't necessarily trick human drivers. For example, this is an example of an attack on an autonomous driving system, where adding this kind of graffiti stuck onto stop signs causes the machine learning algorithm to interpret it as something else. For example, a speed limit sign. So there's this concern that, okay, for autonomous driving, machine learning systems are definitely better than rule-based systems. But in comparison to human systems, we still have these concerns about their robustness against adversarial attacks. And we also have the concern about how they'll generalize to new situations. Okay. Let's look at a different system. Okay, so grading students' essays. Most of you, I guess, have taken the GRE. The GRE uses a combination of human and automatic grading to grade essays on this analytical writing section. Do you think this is a good candidate for machine learning? Okay, take a few more seconds. All right, we're a little more divided here. About a little more than half said this is a good candidate for machine learning. A little less than half said it's not. What makes this a good candidate for machine learning? Okay, so why is grading students' essays good or bad? So Ben says, there are some common patterns and writing errors. So yeah, maybe you can train a machine to recognize those. Evan says it could potentially remove human bias. So a grader might be having a bad day when they grade your paper. Yep, that's true. It could potentially do that. Let's take a closer look at this particular essay. I don't know if you can read this. I'm going to read the first sentence to you. This essay says, careers with corroboration has not, and in all likelihood never will be, compassionate, gratuitous, and disciplinary. Okay, now this is absolute gibberish. This is not a sentence that makes any sense. The GRE essays are graded out of 6. What do you think autonomous grader, a machine learning grader, should give this essay? Well, this essay earned a 6 out of 6. Complete gibberish, absolute complete gibberish. But it turns out that when you ask a machine learning system to train itself on, let's say, many examples of good essays, it doesn't necessarily learn the things that distinguish, that make an essay good. Instead, it learns patterns that are common to good essays. So this system, for example, might have learned that good essays often use advanced vocabulary. And it didn't learn the more complicated pattern, which is that good essays have a clear logical response. Right? So this essay was actually generated by an automatic language generator, and mostly just has, kind of sentences that seem sound but don't make any sense, but has a lot of complicated vocabulary. And the automated grader grades it 6 out of 6. So that's obviously not a good result. Now, another problem here. Imagine you would submit an essay to me in this class, or you submit a project to me, and I give you back the essay or project, and I say, congratulations, you earned a 1 out of 6. And you're very upset because you put in a lot of work. So you say, why did I get a 1 out of 6? And I tell you, oh, I don't know, that's what the computer spit out. Would you be happy with that? So I suspect you would not be happy with that. Okay. So one problem with machine learning systems is they may not be easy to audit or explain their output. Right? And for something like assigning a grade, very often we want to explain the output. So this system is not auditable or explainable. Now, there's a lot of work going into developing machine learning systems that are explainable. But if it's not, that's definitely a disadvantage. Okay. And another disadvantage that we just mentioned is may pick up on a common pattern that's not really what we wanted to detect. Right. So this example, the grader picked up on the common pattern of, high vocabulary, but doesn't necessarily understand emotion, essays that strike human emotion, as Elena said, or it doesn't necessarily understand whether you have a logical or cohesive point of view. Okay. Now, someone mentioned bias. How would you feel if I told you that the essay grading system used by the GRE, it's called E-Rater, actually, on average, overscores students from mainland China compared to human scores by about 1.3 out of 6 points, which means that on average, let's say if students from mainland China would ordinarily get a 4 from human graders, this E-Rater system will give them a 5.3 out of 6 instead. Whereas African Americans are underscored by about 0.8 points out of 6, which means if an African American student submits a essay that might be graded 4 out of 6 by a human rater, the E-Rater will give them only a 3.2 out of 6. Would you be happy with that? Well, if you're from mainland China, you might be happy that it's overscoring your essays because that benefits you. But in general, we don't want machine learning systems to learn some bias. Now, there are a few reasons why there might be bias in the output of a machine learning system. So sometimes it's because it detects patterns that are, let's say, common in the writing from some places and let's say other patterns are common in writing from other places, and it might associate those patterns with positive or negative scores based on other essays they've seen. Whereas those patterns, often appear together with other, let's say, real positive or negative patterns, but are not the reason for them. So for example, maybe the E-rater system learned that African-American dialects are more commonly associated with low scores because it was trained on data where most of the examples from African-American students came from, let's say, a low scoring school district. But that's not a pattern that we wanted to generalize, because of course, then you can have excellent essays that include that same dialect, and you don't want it to underscore this. So there can be a problem of bias where a machine learning system can either perpetuate or exacerbate existing bias in the world, or even create a new bias. On the other hand, someone mentioned that sometimes the machine learning system might offer less bias. For example, if the human grader was having a bad day, well, a machine learning system cannot have a bad day. So this is a kind of it depends situation where we want to be very careful to make sure that our machine learning systems are not either perpetuating or exacerbating or even originating a new bias. Okay, here's another example. So scoring a candidate's performance in a job interview. Is this a good candidate for machine learning systems? So suppose I take the video recording from a job interview, give it as input to a machine learning system that's trained on videos of past interviews and human assessments of those videos. Okay, take a few more seconds. About 3/4 of you said it's not a good candidate for machine learning. Why? Okay, so Farhan says it could potentially be biased. Elena said, yeah, it would generate similar problems as the essay example. Okay, Melissa said, eye contact and expression might be good for machine learning, but it wouldn't be able to judge the content of answers and real personality, which are subjective. But what if I told you that there are, in fact, machine learning systems that are on the market that you can use to score candidates during the job interview? And it doesn't try to score their answers. As Elena said, as Melissa said, that wouldn't necessarily be a good thing. It does score things like eye contact and expression, and it uses them to try and estimate the candidate's personality. So it tells you, for example, if it's a very open or outgoing candidate based on the video. Now, what can be wrong with that? Well, first of all, as Michael said, it's not explainable or auditable. It can also have the same bias problem as the previous essay example we mentioned. One issue here is that it can learn what's called spurious correlations. A spurious correlation is, let's say, when two things appear very often in the training set, the machine learning algorithm will assume it means something when it doesn't. So for example, a bunch of journalists from German public broadcasting tried one of these machine learning hiring systems, and they fed it some videos that they had manipulated to produce some small differences in the video to see whether it would have an impact on the output. So what you're looking at here are, let's say in blue, is a machine learning system scores of the candidate's personality. And then in yellow, it shows what the machine learning system, let's say, predicted about the candidate's personality using the exact same video, but technically modified so it now has a bookshelf in the background. Okay. With a bookshelf in the background, the candidate scores much higher on openness, conscientiousness, extroversion, and agreeableness, and lower on neuroticism. Do you think that's a good result? Okay. Other things that would influence the output of the algorithm were things like a picture frame in the background, whether you're wearing glasses or not wearing glasses, whether you're wearing a headscarf. Now, the company that makes a scoring system said, just like in a normal job interview, these factors are taken into account for the assessment. However, it doesn't happen on demand, meaning it's not, built in. It can appear in talking to real people too. Is this a good answer? Would you be happy to be scored in a job interview by a system that the output depends on whether or not you have a bookshelf in the background or are wearing glasses? I think most of us would not. So a system that learns spurious correlations, meaning it picks up on a pattern that's not really the pattern we wanted to detect, that just happens to be there, well, that can be very challenging. And then, of course, it can also lead to a lot of bias issues, right? Now, another thing, of course, is that it's not really clear that openness, conscientiousness, extroversion, agreeableness are so directly related to job performance. So even if we were able to accurately estimate these things very, very well, it's not really clear that we should use them in hiring, but that's a whole other issue. Okay, let's see what our next example is. So here is a knee x-ray. And suppose we want to train a machine learning system to determine the severity of the injury from a knee x-ray. Is this a good candidate for a machine learning system? Okay, a couple more seconds. Most of you said it's a good candidate for a machine learning system. Do you think this machine learning system might suffer from, let's say, some of the bias problems we discussed with other systems? Okay, some people say yes, some people say no. What would you think if I told you that if you take a set of patients who have a similar score from an expert, so suppose a radiologist looks at this X-ray and determines a score of the severity of injury. Okay. What if I told you that if you look at patients with a similar X-ray score from an expert, among, let's say, all of the patients who have a 4 out of 6 knee injury according to the expert, on average, the Black patients experience more pain. Okay. What might be the reason for that? Well, when a radiologist looks at an X-ray, they're looking for specific features in an X-ray that are known to be associated with a knee injury. And this is based, of course, on medical science, so studies that have been published in journals and made it into their medical school textbooks. And that medical science often comes from very limited study populations. So for example, what we know about knee injuries often comes from studies of miners, people working in mines. And those populations may have been, let's say, not necessarily representative of all kinds of knee injuries. What we're saying is that among the entire world of people with knee injuries, let's draw this. Okay, so we have a world of people with knee injuries. Okay. And maybe some of these people over here. And we'll put some people over here. Okay, so we have this world of people with knee injuries. And medical science happens to focus on the causes of knee injuries, mainly among these people, which means that radiologists are trained to look for the common causes of knee injuries among these people. And they may miss knee injuries among these people because they're not trained to detect it. So what would happen if you would train a machine learning system to predict the radiologist's severity score? Would that be a biased system? So that would be a system that perpetuates the existing bias. Right? It would it would inherit the bias of the data it's trained on. Is there any way to fix this system? Well, this paper comes from an article that does something very interesting. Instead of training the machine learning model to predict the radiologist score, so the problem with this model is not that it was trained only on white data. Okay? The problem with this model is that the radiologists who produce the score that you're trying to learn to predict just miss sources of pain in Black patients very often. So it wouldn't necessarily help to collect more data from Black patients because the radiologists are not producing an accurate score for them. So what this paper did was something very interesting. Instead of trying to predict the radiologist's severity score, it tried to predict the patient's pain from the X-ray. So normally the pain is associated with the severity of injury. So you would expect that someone with a high severity score from radiologists would also have more pain. But we know that that's not true, that Black patients often have more pain than their expert score would predict. So we call this pain disparity. So in order to kind of counteract this bias, this model was not trained to produce a radiology score. It was trained to produce as output, what is the level of pain experienced by this patient? And actually, it was actually reduced the pain disparity, meaning looking at an X-ray, it was able to identify this patient is in a lot of pain in cases where the radiologist would have said this is not a severe injury. So this machine learning system was trained on kind of a different target variable, as we say. And as a result, it was able to counteract some existing bias that humans would perpetuate by being trained on this other source. So we can see that machine learning systems, depending on how they're trained, might sometimes be less biased than a human, but in other situations, it can be more biased than a human. So that's something we want to look out for. Okay, so what are the problems that are good for machine learning overall? Can we kind of summarize what we've learned? What makes something good for machine learning or not? Well, we said it could be less biased than a human. Problems where it's difficult for humans to encode their expertise. Problems where we're concerned about generalizing to new situations, explaining or auditing, or perpetuating existing bias. Those might not be good candidates. Okay. So if we have an accurate and simple algorithm, we don't need machine learning, right? If it's too complicated to explain in a simple algorithm, then machine learning is a good candidate. If there is no good data available to train the model, it's not a good candidate for machine learning. If the model can easily be tricked, if we're concerned about robustness, for example, in the self-driving car example, where there are severe consequences for tricking the model, that might be tricky. And of course, if we need to audit or explain the output, some machine learning models are not very good at that. On the other hand, if we have a problem where the human expertise doesn't exist or is not sufficient, for example, in the knee X-ray problem, the human expertise was not sufficient to identify pain in knee x-rays from, let's say, the minority patients. So this is a good candidate for machine learning. It was insufficient. In cases where humans cannot easily explain their expertise or encode it in a computer program, like the handwritten digit example, this is often a good candidate for machine learning. If you have a solution that's very specific to particular cases, right? So if you have a solution where there are like many different possible cases and you want to be able to have a good output for all of them, that's usually much too complicated to explain in a rule-based system, so it's a good candidate for machine learning. Another example is if you want to know both the answer and the degree of certainty in that answer, often machine learning systems are better at that. And finally, we said way back when that machine learning systems can potentially get more data during operation and improve with experience, whereas a rule-based system will only improve if you manually update it. Okay. So with all that in mind, what's new in machine learning? Well, the statistical foundations of machine learning have been around for decades. And the reason it's exploding now is mainly because of two things. One, the internet. The internet made it possible to collect and distribute huge amounts of data because of all this storage and high quality connectivity. And the second thing that's new is computational power. So with the development of GPUs and other structures that are well suited for certain kinds of machine learning, we can actually do a lot better than we used to do. So let's see, we have a few more minutes. We're just going to talk about a few machine learning basics. I might go a little bit over the hour and a half today, so feel free to leave if you have to. Of course, this is recorded, so you can always watch it afterwards. So let's look at some machine learning basics. Our machine learning system wants to estimate some true value y, so known as a target value variable, for some input x, just like we showed here. Okay, so we have some input x, and we want to estimate some target variable y. Now, we have a few kinds of machine learning. One kind, and these are not necessarily, let's say, strictly orthogonal kinds, but it's useful to be able to make this distinction. Okay. So one kind of machine learning is what we call supervised machine learning. Does anyone know what that is? Okay. So the training data is provided. Now, what's the difference between supervised and unsupervised machine learning? Okay, so it's training based on, okay, so good answer. So I'm going to draw supervised machine learning first. In supervised machine learning, we have some input that's an XY pair. So X is, let's say, the input that we're giving to the machine learning system, and Y is a true value that we're trying to estimate. And all of the previous data that we're using to train the system is also in these XY pairs. So this is a supervised machine learning system. And depending on, let's say, what kind of value Y is, if it's a continuous valued value, like a real number, we call it regression. If it's discrete, like categorical, we call it classification. Okay. Now, that was supervised machine learning. In unsupervised machine learning, it's a little different. We still produce some target variable. Okay. But now, we don't necessarily have the true value of the target variable associated with either the data or the current input. Okay. So in unsupervised machine learning, we still have data that we use to train the system. But now the data is X's only. So in the supervised learning cases, there's some true authoritative Y, and we're trying to estimate Y hat. In the unsupervised learning system, well, we're producing some output, but there's not necessarily a true example. What does that mean? Why would we ever try to do that? what kind of problems will we be trying to solve here? Okay, so here's an example. Suppose we take our example of students' grades on previous coursework, okay? I have a bunch of students in the class, and I want to divide my students into groups for study group sessions, where I want to group together students who have similar backgrounds, who work well together. So I might put together a system where it accepts your grades on previous coursework, and then as output, it gives you an index or a color, a category, right? So maybe the output of the system is, okay, these particular students belong to the orange group, and these particular students belong to the green group. That's the output. So the output is really just the color. Okay. So that's an example of an unsupervised learning system. I don't necessarily have some true values for ideal groups that I'm trying to learn against. I just give it a bunch of data and I tell it, find some natural groups that make sense. This is a problem called clustering. Okay. Another common unsupervised learning problem we'll look at is called dimensionality reduction. Okay. Another machine learning paradigm that we'll take a look at is reinforcement learning. What's different about reinforcement learning? Does anybody know? So reinforcement learning is kind of different in a lot of ways. Reinforcement learning works in kind of an iterative way. It interacts with the environment and it learns from the environment how to respond. What do I mean by that? So the environment gives me a couple of pieces of information. The environment tells me what is the state of the environment right now. And it also tells me how much reward have I earned from my action so far. So for example, suppose I'm using reinforcement learning to play a game, play a video game. So the world is my video game. And at every moment in time, I get some input from the game that's the state of the game. So for example, an image of what's currently on the screen. And it also tells me my reward, for example, my score. And the output of my machine learning problem is an action. So I actually perform an action. And then in the next round, I see, okay, what is my current state and what is my new reward? And then I perform another action. Then I get a new state, a new reward, I perform a new action. What am I trying to learn here? So I'm not trying to learn a target variable. What am I trying to learn? Okay, so I'm learning how to respond. More specifically, let's say we want to learn the expected reward for state action pairs. So I want to know if I'm in a current state and I perform a particular action, what is the expected reward that I'm going to gain? So then I could decide which action I want to take. So that's reinforcement learning. So in most of this course, we're going to concentrate on supervised machine learning. So I'm just going to tell you kind of a recipe for machine learning based on supervised machine learning. And the basic supervised machine learning problem is like this. I have an input sample with a vector of features. So this X is bold, indicating that it's a vector. And I have entries in the vector X1, X2, and so on. And so there's some unknown relationship between this vector of features and a target variable Y. The value of Y is unknown. And we want to find Y hat. Y hat is our prediction for the value of Y, which is unknown to the machine learning system. So I'm going to give you a little recipe for this. And maybe we'll follow along with the recipe by updating this system right here. So let's go back to the system where we were making predictions based on the mean of previous grades. And we'll go through our recipe and, you know, I'm going to do this. Okay. So I'm going to define the system F. I'm going to say y hat, which is our output value, is going to be f of x is going to be W0. Okay. Now let's apply our little machine learning recipe to see how we got there. Okay. First step, we need to get data in some usable representation. And when I say good data, for example, we mean not biased and so on. And we need to be able to represent this data. Now, in this case, we're working with tabular data, basically a spreadsheet. That's very easy. But if we're working with language or sound or images, that might be a little more complicated. But for now, it's easy. So let's say we have our data representation. It's right here. And that is the first ingredient in our machine learning system. Right. And since this is supervised learning, we need labeled examples. I'm just going to copy the labels from. So we have lots of labeled examples, meaning X, Y pairs. Okay. What's next? Step 2. Now we need to choose a candidate model. So we're going to kind of decide in advance what is the structure of fx. So we decided in advance fx is going to be just equal to some value W0. Okay, so here's our model. Next, we need to choose some way of measuring how good our prediction is. This is called a loss function. How should we decide how good our model is in this example? So we're trying to estimate our course grade. How do we know if our estimate is good or bad? Okay, so we could look at some measure of error. So for example, I might look at mean squared error. Mean squared error means I take the difference between each prediction and the true value. So here's the true value. For each example that I feed to the model, or each example in my training set, I'm going to take the difference between the true y and the y hat, and then I'm going to square it, and I'm going to sum those all up. That's called the mean squared error. Okay, so this is a mean squared error for this particular problem. Next, I need to find the model parameter values that minimize this loss function. So here my model has one parameter, W0. I need to decide the value of W0. And I want to choose the value of W0 for which this loss function is minimized. How do I do that? Okay. So the process of finding the W0 that minimizes the loss is called training. So I'm going to use a training algorithm to minimize the loss. And I'm not going to tell you why now, but in practice, the training algorithm should find that the value that minimizes the loss according to the function is just the mean of the y's in the data. Okay, are we finished? I trained an algorithm. I have my parameters. Do I need to do anything else? What do I need to do? Okay, I want to test it. Good idea. So first of all, I'm going to do what's called inference, which means I'm going to give my model new unseen data, and I'm going to tell it to make predictions for the new unseen data. This is called inference. And I'll also do kind of overall evaluation. in which I evaluate the model by computing the loss function of the model for new unseen data. Okay, so here's my basic recipe. Now, what about the example where instead of taking the mean, we looked at the 3 past students who are most similar and we took the median of their grade? Does that have all the same ingredients? Let's see. So in that case, f of x was a median of a set. Our data representation is the same. What was our loss function in that example? Okay, we could use the same loss function. What does training look like if we're, let's say, finding the median grade of the past 3 students who are most similar to us? How do I train that? So in that case, there's no parameters in that model. So in that case, training is actually just storing the data. Farhan says what I want to break it into small segments. So one thing I could do in advance is, let's say, figure out a way to store the data so that similar examples are close to one another. And that would make it easier and faster for me to, let's say, find the set that's most similar to a given input. That would be a good idea, but I don't even strictly have to do that. But I could do that. That would be part of storing the data. Okay, so we've revisited our simple examples, and I'm going to leave you with one thought, a reality check. So we looked at a lot of examples where machine learning does well, a lot of examples where machine learning does poorly. And one thing we want to keep in mind always is that when we're working with machine learning systems and all of these diagrams, I drew my machine learning system as interacting with the real world. I drew my machine learning system as optimizing certain things. Now, it's more accurate to think of machine learning systems as kind of a series of leaky pipelines, or being multiple steps removed from the actual world that we want to interact with. What do I mean by that? So you imagine you have the system F that interacts with the world. And based on interactions with the world, you have some idea of whether it does well or poorly, happy face or sad face. Now, this is what you really want. But in practice, you can't really train a machine learning system on the world. There's very few exceptions. For example, if you're training a machine learning system to play a video game, okay, maybe you could actually train it on the real world. But more often, we're training a machine learning system not on the real world, but on some sort of benchmark task. For example, if we want to train a machine learning system to predict handwritten digits, to, let's say, classify handwritten digits as 0, 1, 2, 3, 4, etc. We're not going to train our machine learning model in the real world. We're going to give it a benchmark data set of digits to learn from. So this is already one leaky pipeline. What do I mean by a leaky pipeline? Well, between the real world and our benchmark task, there are many differences. What are some differences? Well, in the real world, the distribution of what digits look like might actually be very different from the benchmark data set I've collected. What if the benchmark data set I've collected is, let's say, only from people who are, let's say, have English as their first language? It's very possible that our system would be very different if we trained it on a more robust data set that had handwritten digits by people who spoke English as a second language or didn't speak English, right? Maybe people who learned how to write other alphabets. So there's already some difference between the actual world that I care about and the benchmark tasks that I'm training for. Another example is, let's say, the job interview system. There, the world that I'm trying to train for is that I really just want to hire people who are going to do well at their job. But it's not really possible for me to train a machine learning system against job performance. I don't really know job performance for any of my candidates. So instead, I train my machine learning system against a totally different task, which is tell me some basic personality characteristics based on a video input. that bears very little resemblance to the real world I want to, that I actually care about. So there's already a big difference between the world and the benchmark tasks that I train my system against. Okay, that's leaky pipeline number one. What's leaky pipeline number two? Well, leaky pipeline number two is that I can't necessarily optimize even directly on the benchmark task. Right? So I'm not able to train my machine learning algorithm to necessarily be as good as possible on the overall benchmark task. All I can really do is train it to minimize a loss function on a part of the data that I use to train it. So here the leaky pipeline is generalization. So even as far as this benchmark task goes, I might train a machine learning algorithm that does very well in terms of minimizing the loss on part of the data for the benchmark task, but doesn't even do very well for unseen data on the benchmark. So that's the second leaky pipeline. Okay. The first leaky pipeline is the difference between the world and the benchmark. The second leaky pipeline is the difference between minimizing the loss function on some training data in the benchmark between overall minimizing the error on the entire benchmark problem. And then finally, I have another leaky pipeline, which means depending on how complicated my system is, I might not even be able to find the optimal parameters that minimize the loss on the training data in the benchmark. So even beyond the difference between the true world and the benchmark I'm training for, and the difference between the, let's say, overall benchmark and the performance after minimizing the loss on the training set, I also have an optimization gap where I may not even have really minimized the loss on the training set. I might not be able to find the optimal parameters. So all of these steps are kind of leaky parameters. Okay. So that's what I'm going to leave you with today. And over the course of the entire semester, as we look at many machine learning models, we're going to keep coming back to this and try and remind ourselves that when we train a machine learning model, we're not necessarily training it to interact with the real world. And we have these many steps removed from the real world that we actually work with. Okay, I think I'm going to stop here. And let me find my chat.